Welcome everybody to another lecture of second year physical chemistry, and today we are going to talk about the chemical potential of liquids. What will be covered and why? We do a lot of solution work, so we need a way to understand the chemical potential of liquids. What you will need: you'll need Atkinson's physical chemistry. Under the section of simple mixtures, you want to look at the thermodynamic description of mixtures. Mathematics, there's nothing fancy this time round. However, there's quite a bit of logical reasoning. So this lecture, you need to pay close attention to the argument. What we're now going to do is we're going to determine the chemical potential of liquids. So if you now think back to our cylinder example, what we're going to do is we're going to consider the case in which instead of just having a gas, we're going to have a liquid in equilibrium with a gas. Now we know the chemical potential of a gas. We have the results from it from the last lecture. And we are going to make the following statement and say that at equilibrium, the chemical potential for a given chemical species is the same everywhere. With this result, we can write down the following: mu star L, where the L indicates the liquid, we'll get into a moment what the star is for, is equal to the chemical potential of the gas. And since we know from last lecture what the chemical potential of a gas is, that's just equal to mu circle dash plus RT log P on standard state pressure. And again, the pressure here is indicated with a star. The star indicates that you have a system which is pure. You're dealing with pure substances. This equation is a key result. We can know the chemical potential of the liquid if we know the pressure of the gas in equilibrium with it. So basically, all we have to do is, if we want to know the chemical potential of a liquid, is measure the pressure of the gas above it. It's as simple as that. And naturally, you have to also specify the temperature. I'm just assuming for the sake here, room temperature, but it can be any temperature. As I mentioned, the previous result is for pure liquid systems only. That's what that star means. And so that pressure with the star is what we refer to as the saturation pressure of the liquid. Now, life, as usual, becomes quite complex. What happens if we don't have something that is pure? What if, say, our liquid nitrogen is dirty with stuff? And it can be anything. It could be dust particles, could be another material like oxygen, for example. What happens then? Well, let's go back to the chemical potential equation. Remember, the chemical potential of the liquid is equal to that of the gas. So mu L, and it's equal to the gas equation. But you'll notice a subtle difference. That instead of the saturation pressure that we denote with star, there is no star. Basically, if you make something dirty, the pressure has to be different because the chemical potential of the system must have changed. So, in short, the pressure of the gas is going to be pressure, but it's not going to equal the saturation pressure. Now, if you take the previous two equations, the one on this slide and the previous slide, rearrange the two, you will get a general equation that looks like the one here at the bottom of the slide. And I'll just read it out. The chemical potential of a liquid is equal to the chemical potential of the pure liquid plus RT log pressure divided by pressure star, the saturation pressure. And so what we've essentially done is we have rewritten the chemical potential for a liquid, for a general liquid, in terms of its pure state, the liquid pure state. But the cost is that the denominator in the logarithm is not the standard pressure, which is usually 1 bar, but now the saturation pressure. All right. With that in mind, we now have enough conceptual machinery to start tackling solution chemistry. So here in the middle, we have a beautiful artistic impression of a beaker and a solution. It has a solvent and it has a solute. So we have a dirty liquid. What we can do is we can write down for the liquid, the solvent, the chemical potential, as from the previous slide, and is indicated here on the left. And what we're going to do is we're going to just follow a key experimental result, which was discovered by a gentleman of the name Rolt. And what he discovered was the following experimental relationship, which is to say that the pressure of either the solvent or the solute is equal to the mole fraction in the solution multiplied by the saturation pressure. This is something that was just observed to be true. Now, it's not true in general, as we'll find out, but for systems that are where solutes and solvents have similar chemical structures, this is the relationship that was observed. With this equation, what you can do is you can rewrite the chemical potential by doing a very simple substitution. You write chemical potential of the liquid is equal to its pure state, now, plus RT log mole fraction. And the key thing here is to keep in mind that with solutions where the solvent and this solute both obey this equation, the rewritten chemical potential in terms of mole fraction, if both the solvent and solute obey this equation, we are dealing with what is called an ideal solution, or they are called ideal solutions. So you need to burn this into your memory. If you see the bottom equation and it is stated that both the solvent and solute obey this equation, you are dealing with an ideal solution. Alright, so who's Rolt? Francoise Marie Rolt. There he is. Magnificent beard. I wish I could have something like that myself. Dressed in very much 19th century clothing. Guy was born in 1830, died in 1901. He was a Frenchman who worked on the physical properties of solutions. He also did work on electrochemistry. His work led to methods to determine the molecular weights of dissolved substances. And he was quite well known between the physical chemists of that time. As usual, life becomes even a bit more complex. Is you can get something called the ideal dilute solution. So, what is it? Well, basically, it's a solution that is not ideal. So remember, an ideal solution is where both the solvent and solute both obey the chemical potential equation that's dependent on mole fraction. What happened is Henry discovered another simple relationship that gives some sort of idealized behavior. It was a bit different, very closely related to Rolt's equation, and he found that for some solutes, that when a solute is dilute, you get the following relationship. that the pressure of the solute is equal to the mole fraction of the solute in the solution multiplied by some constant K, where K has got the units of pressure. But note, it is not the saturation vapor pressure, it's some other number. A solution in which the solute behaves according to Henry's observations and the solvent is ideal. We are dealing with something called the ideal dilute solutions. And basically what I've written down here at the bottom is to state that in the limit of the mole fraction becoming 0, that's just to say it's becoming dilute, the chemical potential of your solute is equal to its pure state chemical potential plus RT log xk on P star. You do rearrangements and you get a final equation which you can rewrite only in the case of the dilute condition, mu circle plus RT log x, where x is the mole fraction. Mu circle is just a way of gathering all the constants which is in the front, in the middle equation, together under one heading. And in this way we can actually distinguish this equation from an ideal solution by looking at this constant offset. Alright, who was Henry? William Henry. I guess his friends called him Bill. He was born in 1774, Manchester, and he died in 1836. And he very much has got the clothing of a 18th century gentleman. He apprenticed for a guy named Thomas Percival, who developed medical ethics. And he himself wanted to be a medical doctor, but due to ill health worked on chemistry. And his work on dissolved gases in water led to what we now know as Henry's Law. He was a fellow of the Royal Society, so he was a bit of a heavy hitter, but sadly he shot himself in his private chapel in 1836. So the key concepts to take away. There's two things. Ideal solutions. That's where the solute and the solvent obeys Raoult's law. And you can write its chemical potential instead in terms of its mole fraction and the chemical potential of the pure state. In ideal dilute solutions, the solvent's ideal, but the solute obeys Henry's law, and hence for the solute you can rewrite the chemical potential in terms of Henry's constant at the bottom here. Alright, now for the quiz. There's 4 questions. You are going to do numerical calculations, and I'll read it out for you. Question 1. The standard state chemical potential of nitrogen is 0 joules per mole. A flammable solution is in a nitrogen glove box. And nitrogen glove boxes are usually put at 1 bar pressure, basically 1 atmosphere, at room temperature, and we do so to prevent a fire. However, nitrogen has dissolved into the solution. What is the chemical potential of the dissolved nitrogen in the solution? Give the answer in joules per mole. Question number 2. From question number 1, can you deduce and tell me whether there's no chemical energy due to nitrogen in the flammable solution? There is no chemical energy or there is chemical energy. You need to decide. Question 3. I have an ideal solution. My standard state chemical potential for both solute and solvent is 0 joules per mole, and my mole fraction is 0.5 for the solute. What is the chemical potential at room temperature? Give the answer in joules per mole. For question 4, what I want you to do is the same thing as in question 3, but to do it for the solvent at room temperature. Give the answer in joules per mole.